Okay. Also, there's the handouts up there. The handouts in class are also on Canvas, and it's really just a derivative worksheet and then all of the answers. So if you're looking for more practice, I'll point out they're not solutions. They don't go step by step. They just tell you what the answer is. I'm always happy to talk about anything on that sheet if you want to, but if you're looking for more practice or another resource where you can try a problem and then see what the answer is supposed to be, that's there for you. And it's also on Canvas. So let's go and look at these first few problems, and we'll start talking about all the things. We have a lot of things to talk about. For f of x equal to 7 times sine of x, the derivative is going to be 7 times the derivative of sine of x, which is cosine of x. Or as I would say in general, if you have a constant multiple of a function and you take the derivative, the constant multiple hangs out. So you get the derivative of 7 times sine is 7 times the derivative of sine. On the other hand, here for g of x equal to cosine of x plus 6, the derivative is going to be, well, the derivative of cosine of x is negative sine of x, and the derivative of 6 is 0. And I wouldn't really write plus 0, I would just write this is equal to negative sine of x. So when you have constants on their own, added or subtracted, their derivative is 0. When you have constant multiples, they stick around. So this last one here. So I'm going to do one extra thing here. If I want to find, so I'm just pointing out here some different notation, right? You can say, here's my function g of x, find the derivative of g prime of x. But you can also write, find d dx, the derivative of this whole function. So I'm going to write this in a slightly different way. I know it's going to be 18x squared, but I'm going to write it as 6 times 3x squared plus 2 times the derivative of sine is cosine minus 4 times the derivative of cosine. I'm going to put some parentheses here so it doesn't look like 4 minus sine. I'm going to write 4 times negative sine of x plus 0. And if I felt compelled to simplify this, I would write this as 18x squared plus 2 cosine of x plus 4 sine of x. And that's how I write my derivative here. Okay, so yeah, let's keep going. So we kind of need to talk about all the derivative rules we need to know, because there's a few of them and you kind of have to memorize some of them. So, well, really kind of all of them. We've talked about the product and the quotient rule. I'm going to, did we talk about the quotient rule? Yeah, we did. No, we didn't. Okay, so, all right. So here's what we've got so far. We've got the power rule, which is that the derivative of x to a power is equal to that power times x to that power minus 1. Works for any real number. P is any real number. We have the product rule, which is that the derivative of f of x times g of x is equal to f prime of x times g of x plus f of x times g prime of x. Great rule. I'll point out, no, I won't. And then we have the quotient rule, which I would say is very similar to the product rule. The top part of it looks almost exactly like the product rule. So we want to take the derivative of f of x divided by g of x. It's going to equal, here's how I say it in my head. I'm going to write it and I'll tell you how to say it. It's going to be f prime of x times g of x minus f of x times g prime of x, all divided by g of x squared. When I think about, when I think about the quotient rule, what I really say in my head is I say that it's the bottom function times the derivative of the top minus the top function times the derivative of the bottom, all divided by the bottom function. Question, Shereen?
Is the value P is any value?
P can be any real number. Yep. Sorry, I know my writing is not always great. Yeah, that was better. Yeah. So let's talk about these So these rules, we definitely want to kind of practice until you know them by heart. And your next couple homework assignments, there's definitely like a bajillion problems on them. So you're gonna have lots of practice. But let's do a couple examples. Let's say we want to find the derivative of x squared plus sine of x over x cubed. X cubed plus 4. So if I'm trying to find the derivative of this using the quotient rule, you can write some extra steps. I don't like to because I've done it for so long. But the steps you can write first is just gonna be, okay, well, it's gonna be the bottom function times the derivative of the top. I will point out, I am doing this not out of order necessarily, right? No, on the top, I wrote f prime times g, and here I'm doing it is g times f prime. That's just the way I've always done it. Doesn't matter what order you multiply things in this, so it's okay to do it either way. You can either do it as f prime times g or g times f prime, doesn't matter. Minus the bottom, I bottom derivative top minus top times the derivative of the bottom. X squared plus sine of x times the derivative of x cubed plus 4. All divided by the denominator squared. Now we can't just leave it like that because we haven't actually taken the derivatives of those things here and here. So we're going to do another writing of this, and we're going to have x cubed plus 4. We do need these parentheses. They're absolutely vital. Times the derivative of x squared plus sine of x, which is 2x plus cosine of x, minus x squared plus sine of x, also in parentheses. And then the derivative of x cubed plus 4x is 3x squared. And technically, you don't need parentheses around that. It's only one term. Still not, it's not wrong to write them if you want to, but if you don't have it added something else or subtracted or something else, you don't need parentheses there. All divided by x cubed plus 4 squared. And that's where I would leave this. I wouldn't multiply out the top part and cancel things if I don't think anything cancels really, but usually we're not so concerned with simplifying these right now. Why don't you all try the following one? F of x equal to x squared over x to the 6th plus 3, find f prime of x. All right, let's see what we've got. So sometimes you can do it like this. I personally like to save space when I'm writing, especially because I always run out of space. So if I'm thinking about doing the bottom times the derivative of the top, here's what I'm going to write. I'm going to write out the bottom function, x to the 6th plus 3, times the derivative of the top, which is 2x, minus the top, times the derivative of the bottom, and the derivative of the bottom is going to be 6x to the 5th. All divided by x to the 6th plus 3 squared. And we're done. Yeah, we can simplify that. We don't really want to simplify. I will say we don't want to simplify it unless we are being maybe asked to find a second derivative. Yeah, we might. Let's go. We're going to find a second derivative. We're going to simplify this. So normally we wouldn't, but if we are finding a second derivative, we really don't want to leave that as is. So continuing on here, if I multiply out the top, I'm going to have 2x times x to the 6th, 2x to the 7th, 3 times 2x is 6x, and x squared times 6x to the 5th is minus 6x to the 7th, all divided by x to the 6th plus 3 squared. And it definitely is going to pay here to simplify this and say that 2x to the 7th minus 6x to the 7th is negative 4x to the 7th. So I should write this as 6x minus 4 times x to the 7th, all over x to the 6th plus 3 squared. And we're not going to take the derivative of this just yet because we haven't talked about the chain rule yet. We can't quite just yet. We'll come back to that. Get one more, and then we'll move on talking about some other trig things. Let's say our function was g of s equal to s to the 4th times sine of s all over s cubed plus 1. Now I want to take the derivative of that. And yeah, we're going to use some different variables because sometimes your web work likes to use different variables. Not my favorite, but it is good to practice getting used to seeing other letters as variables. Also, sometimes other letters are constants. All right, so let's see here. All right, here I am going to write it out kind of a long way. Bottom times the derivative of the top. Ooh, the derivative of the top looks complicated. Let's just write it as s to the fourth times sine of s with the prime. We'll come back to that in the next step. Now minus the top, s to the fourth times sine of s times the derivative of the bottom, which I think the derivative of the bottom is simple enough. We can just do it. It's 3s squared. All divided by the bottom squared. Okay, so now to take the derivative of the part here, the s to the fourth times sine of s, what rule do we have to use? Right. If you're saying something times something else, it's a really good indicator that we have to use the product rule. So g prime of s is going to equal s cubed plus 1 times, so here I have to use the product rule. So it's the derivative of the first piece, 4s cubed times the second piece left alone, plus the first piece, s to the fourth, times the derivative of the second piece, which is cosine of s. And then minus all of this, s to the fourth times sine of s, all times 3s squared, all divided by s cubed plus 1 squared. A little messy. That's all right. So definitely practice as much as you can the product and the quotient rule, because you're going to be using them all the time, and you're going to be using them next quarter, right? Like you definitely need to be able to differentiate things really well, because next quarter when we start talking about anti-derivatives, we really need to know how to take derivatives to understand how to undo them. So definitely, as I was saying to people earlier today, the derivatives part of this course is really kind of a big part, even though it's getting covered pretty quickly here. These rules, the derivatives of trig functions and e to the x, and not log of x, and power rule, product and quotient and chain rule, that is the stuff that you will probably use the most of next quarter. So definitely spend some time really practicing it, doing a lot of as much. I mean, I know there's lots of homework problems, so you probably got lots of practice. If you run out of practice, there's more practice right there. Okay, let's talk about a couple more rules that we need to memorize. Specific function rules. So we have the derivative of sine of x is equal to cosine of x, and the derivative of cosine of x is equal to negative sine of x. And I did see that I think it was the last class or the class before, she did show the limit definition of the derivative of sine of x, which we could go over, but I don't think it's particularly valuable. I mean, it's not valuable. But let's talk about the other trig derivatives, and if you really want to, we can go back and come back and talk about sine and cosine. So I want to know what the derivative of tangent is. I'm going to leave myself some space here because I'm going to kind of fill in all the trig derivatives right here. That's probably enough room up there. So to find the derivative of tangent, well, we're going to write it as sine over cosine. I should say we're going to write it as the quotient sine divided by cosine. And then if you're trying to take the derivative of a quotient, we're going to use the quotient. So it's going to be the bottom times the derivative of the top, and the derivative of sine is cosine, minus the top times the derivative of the bottom, and the derivative of cosine is negative sine, all divided by the denominator squared, cosine squared. But then on top, we have cosine times cosine, which is cosine squared x, minus sine times minus sine is plus sine squared x. And cosine squared plus sine squared is equal to 1. That's a trig identity. And while 1 over cosine squared is correct, the more typical way of writing this derivative is secant squared of x. So the derivative tangent of x is secant squared of x. Kind of great. And what's really great, yeah, I'm going to say, okay, I'll say a couple things. Let's do it for cotangents as well. Cotangent is virtually the same process. And we're going to do all the rest of them, and then we'll talk about some patterns that I think are worthwhile to see to help you remember them, or actually to help you remember less. So if I want to do cotangent, it's going to be the derivative of cosine of x divided by sine of x. Okay. Again, the quotient rule. I want you all to write it out. Write out the next step. All right, I'll give you the bottom. I'll give you 30. All right, we should be getting the bottom, which is sine, times the derivative of the top, which is negative sine, minus the top, which is cosine, times the derivative of the bottom, which is cosine. So here we end up getting negative sine squared x minus cosine squared x all over sine squared x. If we factor out a -1 from the top, you've got -1 times sine squared x plus cosine squared x all over sine squared x, which just ends up being -1 over sine squared x, or more typically written as negative cosecant squared x. And yeah, I want to write that one. I'm going to write that one down here. So there's a usual pattern for the way we write the 6 trig derivatives. I'm going to write it in the usual way. We usually write each co-function each reciprocal function next to the function of the reciprocal. So to the right of sine, I'm going to eventually write the derivative of cosecant, because cosecant is the reciprocal of sine. And to the right of cosine, I'm going to write the derivative of secant, because secant is the reciprocal of cosine. And finally, to the right of tangent, I'm going to write the derivative of cotangent, which we just found, which is negative cosecant squared of x. All right, let's do secant, and then we'll talk about, we may or may not actually do cosecant, we'll see. Secant is actually in some ways easier than than tangent and cotangent. For secant, we have to know that the derivative of secant of x is the derivative of 1 over cosine of x. Now we're going to use the quotient rule one more time. So we get the bottom, which is cosine of x, times the derivative of the top, which is 0, minus the top, which is 1, times the derivative of the bottom, which is negative sine of x, all divided by the bottom squared. Okay, let's simplify this a little bit. So I've got 0 minus 1 times minus sine is positive sine. So I have sine of x divided by cosine squared of x, which is technically a correct way of writing this. And no one I've ever met has ever said the derivative of secant is sine divided by cosine squared. Instead, what we do is we rewrite this as 1 over cosine of x times sine of x over cosine of x, which is the same, right? Top times top is sine, bottom times bottom is cosine squared. And then 1 over cosine is secant of x, and sine x over cosine x is tangent of x. So the derivative of secant of x is secant of x times tangent of x. Now, we're going to do the last one, but I want to point out a pattern to you that I have found useful. And it's kind of the pattern of any derivative that works, you can also add a co to each trig function and the derivative still works. Here's what I mean. So just listen for a second. The derivative of tangent is secant squared. Cool. So the derivative of co-tangent is co-secant squared with a negative sign. The negative sign is coming in. Okay, the same kind of thing works for secant. The derivative of secant of x is secant of x times tangent of x. The derivative of co-secant of x is co-secant of x times co-tangent of x. You just add a co-prefix to each trig function, and then you slap on a negative sign. So the derivative of cosecant of x is really, well, instead of being secant going to secant tangent, it's cosecant going to cosecant, cotangent with a minus sign. It even technically works for sine and cosine if you know that cosine is really just sine. Derivative of sine is cosine. Derivative of cosine is cosine, sine. But it's a little shaky there, so I don't like to say that one. But we could actually show it. The derivative of cosecant of x is the derivative of 1 over sine of x, and then quotient rule, bottom times the derivative of the top minus top times the derivative of the bottom, all over the bottom squared. That just ends up being negative cosine x over sine squared x. We break it up in a similar way as before. It's negative 1 over sine times cosine over sine, which is really just negative cosecant x times cotangent x. So here are your 6 trigonometric derivatives. I highly recommend memorizing them. I cannot recommend it enough. They're going to keep coming up. They're not going away. What I would actually recommend doing is making it the background of your phone. That is what I've done for other things I've had to memorize that just would not stick in my head. I've made them or that more the lock. I think the lock screen is actually better because you see the lock screen right away. Make it the lock screen, be like, oh, there's my trig derivatives. Let me think about them for a second and then do whatever you do. But I recommend memorizing all of these. Yeah. Which way do you want to go now? Any questions, by the way, before I keep going? Questions? Okay. So then we can start to ask more complicated questions about derivatives, like what's the derivative of x to the 5th times tangent of x? And I have to know the derivative of tangent off the top. Okay, so that's going to be product rule. Sometimes I like to, when I'm writing the product rule, I actually like to call each thing like f and g. I can call that f, that g. Like, okay, it's going to be f prime times g plus f times g prime. There's nothing wrong with writing that down. So then f prime is going to be 5x to the 4th. G is just tangent plus f, which is x to the 5th, times g prime. And the derivative of tangent of x is secant squared of x. Oh, I remember the other thing I want to show you all. One time a student of mine showed me a way they remember it, which I think is kind of cool. I don't know, it works for them. They did this. They said, James, I like to do this. They say tangent, right arrow, secant, left arrow. So what they're doing with this is they're saying the derivative of tangent is secant times secant. The derivative of secant is secant times tangent. And you can also do it for cotangent x with negative cosecant x and cosecant x. Derivative of cotangent is negative cosecant times cosecant. Derivative of cosecant is negative cosecant times cotangent. It worked for them. It was like a fast thing they could write down like on the beginning of their test to help them be like, okay, I can just look at this and know what my derivatives of tangent and secant and cotangent and cosecant are. Not at all required, just things that work. I like it. It's not bad. Why don't you all try this one? Find the derivative. Ooh. Actually, don't try this one. We're doing this one together. Let me show you a useful trick. Let's say I want to find the derivative of secant of x divided by x cubed. I'm a fan of avoiding the quotient rule when it makes sense to. And here you could totally avoid the quotient rule if you decide to rewrite this as the derivative of x to the negative 3rd times secant of x. You're still going to have to use the product rule, but most people tend to prefer using the product rule. That said, you still need none. So here, if we write it this way, we're going to get, let's see, the derivative of the first thing, which is negative 3 times x to the negative 4th. Leave the second thing alone. Add, and then we switch it up. Leave the first thing alone. Multiply by the derivative of the second thing, which is secant of x times tangent of x. just for the sake of showing you, if we'd done it using the quotient rule, you would have gotten the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. And this might look pretty different, but x cubed over x to the 6 gives you an x to the negative third, and there's your x to the negative third times secant times tangent, and 3x squared divided by x to the 6 gives you a 3x to the negative fourth, so you get a negative 3x to the negative fourth times secant x. So they really are the same, just different ways of writing it. Okay, I wish I had more time. I mean, I know we got still like a lot more time, but there's a lot of things to say. So here's what I will move to next. Let's go ahead. Let's talk about the chain. Chain rule is kind of a big deal. And actually, let's start off talking about the product rule. Product of many things. So let's say, for example, I want to define the derivative of, sure, x squared times sine of x times tangent of x. Yeah, x squared, sure. It's kind of annoying. So let me show you how you might do this just generally. I'm going to think about this as a product of two things. I've got this thing times this thing. It doesn't actually matter which way I break it up. You could have broken it up as x squared times sine x tangent x. I'm just picking one. And now I'm going to use the product rule. And I'm going to be very kind of showing all my steps. So it's going to be the derivative of the first part times the second part plus the first part times the derivative of the second part. Okay, good so far. But now check this out. For the derivative of x squared times sine, we have to use the product rule again. So for here, I'm going to say, well, the derivative of x squared times sine, it's going to be the derivative of x squared times sine of x plus x squared times the derivative of sine of x. All of that times tangent of x plus x squared times sine of x. And I might as well take the derivative of tangent since I can. Derivative of tangent is going to be secant squared of x. And now the derivative of x squared is 2x times sine of x. And then I'm going to multiply the tangent as well. And then I've got x squared, derivative of sine is cosine times tangent. I'm not going to simplify that, but I'm going to point out that cosine of x times tangent of x is really cosine times sine over cosine. And you get to cancel the cosines and just get sine. Normally that would be a good thing to do, but I don't want to do it here because I want you all to see something. Plus x squared times sine of x. Here's what I really want you to see. And I know I mentioned this pattern at the end of class on Thursday, but I know it's been like 5 days since I've seen you all. So let's re-talk about it. So if I think of this first piece as F, the second piece as G, and this third piece is H, what I'm really getting at the end here is F prime times G times H plus F times G prime times H plus F times G times H prime. And that idea holds no matter how many pieces we are multiplying together. So for example, we're not going to actually do it, but if you wanted to find the derivative of, say, F times G times H times K, you're going to get 4 pieces. And each piece is going to have one of the derivatives and the rest not derivatives. That would end up being F prime times G times H times K plus F times G prime times H times K plus F times G times H prime times K plus F times G times H times K prime. Why would we care about this? Well, because it's going to lead us to the chain. That's why we actually care about this, is because we're going to see from this example the chain. So let me show you what I mean. Oh, that's not the straightest line I've ever drawn. Oh, wow. Let's say we wanted to find the derivative of, do I want to do it that way or that way? Let me think for a second here. Yeah, let's do it that way first. Let's say we want to find the derivative of x. Let's say 2x cubed plus 1 cubed, James, really? To the third power. Not taking my choices here. That's fine. So here's how we're going to do this. We're just going to multiply it out. We can totally multiply out something cubed, but remember I talked about Pascal's triangle? We made the list of like 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. This is like x plus h to the third, except it's this plus this to the third, and you're going to get right, a plus b to the third is a cubed plus 3a squared b plus 3ab squared plus b cubed. So when you multiply this out, you get, well, the first thing cubed, I'm taking the derivative of 2x cubed, and then 3 times the first thing squared times the second thing, which is 1, plus 3 times the first thing, the first times 1 squared, and then finally plus 1 cubed. All right, so let's simplify before we differentiate. Always a good rule of thumb. 2x cubed is really 8x to the 9th. And 3 times 2x cubed squared is 3 times 4x to the 6th, 12x to the 6th. And 3 times 2x cubed is just 6x cubed. All right, so now we're going to differentiate. When we do this, we're going to get 72x to the 8th plus 6 times 12 is also 72, x to the 5th. And 6 times 3 is 18x squared. Yep. And then the derivative of 1 is 0. And this may not look very interesting, but it is. We just need to do a little bit of factoring. So let me factor out as much as I can here. Let's say, let's think I can factor out an 18. See, 18 times 2 is 36, and 36 times 2 is 72, sorry. So yeah, if we factor out an 18 and an x squared, we're left with 4x to the 6th plus 4x cubed plus 1. Okay, now check this out. I'm going to break this up just a little bit, and there's a reason, which I'll tell you in a minute. I'm going to write this as 3 times whatever's in parentheses here, and then I'm going to write the 6x squared at the end here. Just to help us see the thing I want us to see. But right, 3 times 6x squared is definitely 18x squared. Okay. And then this factors. This definitely factors as 2x cubed plus 1 quantity squared. That's just 2x cubed plus 1 times 2x cubed plus 1. And so here's what it looks like I've actually done. I've said I have the derivative of something cubed. And what I ended up with was 3 times the same something squared times the derivative of the inside something. And that is the very essence of the chain. Okay, so let's get a little bit more general. If I want to take the derivative of some function raised to the nth power, or the p, I guess I use p. P is what we've been using. Let's use p. Here's how I usually think about the chain rule. If I've got some function inside of another function, I'm going to ask myself, well, what if I just had x to the p? The derivative of x to the p power is p times x to the p minus 1, just the power rule. Well, I'm going to replace x with that. So I'm going to say the derivative of x to the p is p times x to the p minus 1, right? I know that. So the derivative of my function to the p is going to be p times my function to the p minus 1. But then I have to multiply by the derivative of the inside function, the derivative as the stuff, as I will often say. Which seems pretty reasonable, but let's actually, I really feel like you deserve an explanation here. It's nice to see an example and kind of believe it's true, but let me give you an explanation because I would want one. So let's say we're going to do this. So the derivative of f of x to the p. We're not going to use the limit definition. We're going to use a repeated product rule because f of x to the p really means f of x times f of x times f of x times f of x p times. So what I'm really doing here is the derivative of x, 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 f of x, p times. And here is where that idea of the repeated product rule is going to come into play. We're going to say, well, okay, I'm multiplying p things together. So just like before, when I was multiplying 4 things together, I got 1, 2, 3, 4 pieces, and each piece had one derivative and the rest not derivatives. So when I do this, I'm going to get p things added together. The first one is going to be f prime times f times f times all the rest of the f's. How many f's are there that are not f prime? Ooh, how many? Well, let's see. There were p of them. Now there's how many? One less. Right. So that's going to be p minus 1. And then the next one is going to be f of x times f prime of x times f of x all the way to the last f of x. But in here, there's still p minus 1 f of x's multiplied together. They just are not all at the end. Each one of the things we are adding together is going to have exactly 1 f prime times p minus 1 f of x's. Until the very last one, which will be f of x times f of x times f of x all the way to f prime of x being the last one. And here you have still p minus 1 f of x's. Okay, how many things am I adding together? Well, when I did the derivative of a product of 4 things, I added 1, 2, 3, 4 things together. When I did a product of 3 things, I added 1, 2, 3 things together. Whatever the number of things multiplied together is the number of terms we're adding together. So I have 1, 2, 3 p terms. So look what I've really got. Oh, and they're all the same, right? Each of these is 1 f prime times, in fact, let me rewrite this. I've got f prime of x times f of x to the p minus 1, plus another f prime of x times f of x to the p minus 1, all the way to the last one, which is another f prime of x times f of x to the p minus 1. But if you're adding the same thing over and over and over again, right? If I add x plus x plus x, I get 3x. If I add this plus this plus this that many times, p many times, I get p times f prime of x times f of x to the p minus 1 power. Whereas I would prefer, I would write this as p times f of x to the p minus 1 times f prime of x. So when you have some function inside of another function, you do the derivative of the outside function, you leave the insides alone, and then you multiply outside by the derivative of what was inside. Let's do a few examples here. So, all right, it's a little fast start. Okay. So we want to find like the derivative of x to the 4th plus tangent of, I go to tangent, and too much tangent, sorry. The 6th power. Sorry, I was like talking to myself while I read that. Let's read that again. The derivative of x to the 4th plus tangent of x to the 6th power. So when I'm looking at this, when you're looking at this, what I really want you to think of is you have some stuff raised to the 6th power. And the derivative of some stuff to the 6th power is going to be 6 times that stuff to the 5th power. But I said the magic word stuff, which means I have to multiply by the derivative of the stuff. So I have the 6 times x to the 4th plus tangent of x to the 5th times the derivative of x to the 4th plus tangent of x. And it's totally fine to skip the step of writing the derivative of the thing and really just saying it's going to be whatever that derivative actually is. but it's also perfectly fine to write this intermediate step if you prefer. So we're going to get 6 times our stuff, the 5th power, times the derivative of my stuff is going to be 4x cubed plus secant squared of x. All right, your turn. You want to try finding the derivative of 6 cosine of x plus x to the 4th, x to the 4th again. How about x to the 40th? All to the 9th power. Give that a try. All right. So I have some stuff to the 9th power. I know, and so really what I'm also thinking about when I do this is I'm really being like, okay, what's the derivative of x to the 9th? It's 9x to the 8th. So there's some stuff to the 9th is 9 times my stuff to the 8th. The stuff is just taking the place of x. And then we're going to multiply by the derivative of the stuff. Welcome, come on in. In this case, the stuff is 6 cosine of x plus x to the 40. And the derivative of that stuff is -6 sine of x plus 40x to the 39th power. Not at all necessary to write that this is the stuff, but it does help me see what I am doing. Just like with most things, if your derivative of your stuff, or when you're in your product rule, you've got more than just one term, you need parentheses around it so that we are really saying it's this times all of this. Just to kind of find it, if I hadn't written parentheses here, or if I'd written it like this, 9 times 6 cosine of x plus x to the 40th, the 8 times -6 sine of x plus 40x to the 39th. They might just think I'm multiplying only by -6 sine of x. That is not what we want to be true. So we need those parentheses. It can get more complicated. For example, maybe we're doing something like the derivative of sine of x plus 6 over x cubed, all raised to the 12th power. And then, well, the same idea is still applicable. You still have some stuff to a power. And the derivative of some stuff to a power is going to be, well, in this case, the power is 12. So it's going to be 12 times that stuff to the 11th power. And then we have to multiply by the derivative of the stuff. Sometimes, depending on how complicated it looks, I will just write the stuff with a prime on it, and then in the next step, take its derivative. But you don't have to do it that way. You can always be like, yeah, I know how to take the derivative of that. But you do have to, you can't leave any primes in, well, that's okay. If it's regular differentiation where you're just finding a derivative, not implicitly, you can't leave any primes in your answer. You have to finish it off by actually finding the derivative of the thing you've written the prime on. So here we're going to get 12 times our stuff. Whoops. The 11th power times, oh, gotta use the quotient rule here. This is going to be the bottom times the derivative of the top, which is cosine, minus the top, which is sine of x plus 6. I do want parentheses around that, times the derivative of the bottom, which is 3x squared, all divided by the bottom squared, which is x. Yeah. So you can have any kind of amalgamation of the product, the quotient, the chain rule, all kind of rolled into one. It can be messy. So chain rule is great. And it works really for not just functions raised to powers. Meaning, yes, as I would, so when I look at this, I think of the outer function as being respectively raised to the 6th power, raised to the 9th power, raised to the 12th power. And then the inner function is just whatever the stuff is on the inside. But you can have your outer function be any function. So what I'm really trying to say here is, and let's start off with a really easy example. We can use the chain rule to take, say, the derivative of sine of 2x. And let me show you, we're not going to like prove this one, but I'm going to show you a picture to justify why this should be what it should be. So let's think about it. Before, when we talked about the derivative of sine of x, we graphed it. And we said, okay, sine of x has a period of 2 pi, has an amplitude of 1. And I'm graphing sine to start off with, not sine of 2x just yet. Just graphing sine of x. It looks kind of, it looks like this. Pretty much. And then we said we could find the slopes of the tangent lines. So the tangent line is 1, and then 0, and then -1, and then 0, and then 1. We say this is y equal to sine of x in black. Down here below, you can draw the derivative, y prime, and the value is 1, and then 0, and then -1, and then 0, and then back to 1. And that looks a whole heck of a lot like cosine. And it is. Great. Okay. So let's do the same sort of thing, but now for sine of 2x. So for sine of 2x, I'll draw in green. I don't know if you can actually really see the difference in colors there, but oh yeah, you kind of can, right? Yeah, okay. So the only difference between sine of x and sine of 2x is that sine of x has a shorter period. Right here, the period for sine of 2x is 2 pi divided by 2 instead of 2 pi divided by 1. So we get the whole sine cycle to happen from 0 to pi. So we're going to start here, we're going to end here, and then we're going to cut that up into 4 equal sections. So cut it in half at pi over 2, and cut those each in half again at pi over 4 and 3 pi over 4. So it's going to look like this. Let me zoom in a little bit because I feel like this we want to be really kind of, yeah. So we're going to get at pi over 4, we're going to get a high of 1, and then at pi over 2 back to 0. 3 pi over 4 down to -1, pi back to 0. So it looks like that. That's pretty good. Okay. And now I'm going to use the same technique to draw the derivative. Notably, get really zoomed in. At right here for this green graph, the slope of the tangent line is steeper than it was before, right? For this original one, the slope was 1. For this one here, the slope is definitely steeper, and I'll tell you it's 2. There's my derivative. And then over here at pi over 4, the slope of the tangent line is 0. Over here at pi over 2, the slope of the tangent line is steeper than over here. It's -2. And then over here, it's going to be 0 again. Finally, back here at pi, it's going to be steep again. It's going to be 2. So check this derivative of sine of 2x out. It definitely looks like a cosine function, but I've done 2 transformations to it. I have also shortened its period. This looks like cosine of 2x as opposed to cosine of x, but I've also stretched out its amplitude. So instead of being just cosine of 2x, it's 2 times cosine of 2x. Or as I would prefer to write it, y prime, is that right? Yeah, is equal to, kind of dying, it's crazy. Cosine of 2x times 2. Or in other words, the derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff. The chain rule works for any kind of composition of functions. We just have to get used to identifying what's on the inside and what's on the outside. So when I look at this, I say, oh, sine is my outer function. I take its derivative, I leave sides alone, but then after that, I have to multiply by the derivative of the inside. So here is the chain rule written as a rule. I don't know how much you really need to. It's a perfectly fine rule. People often write that the derivative of f of g of x is equal to f prime of g of x times g prime of x. Or as I would say, the derivative of a function of some stuff is you take the derivative of the outer function, you leave the inside stuff alone, and then at the end you multiply by the derivative. So the argument of your function or the inside part of your function is any more complicated than just x. And even if it is just x, at the end you're always going to multiply by the derivative of the inside. We've been doing this whole time. It's just that the inside has always been x, and so the derivative of x is just 1. But really, we are always using the chain. I actually want to think about it that way. We got time. Let's look at some more examples. Let's say we want to find the derivative of now something like cotangent of x to the 4th plus sine of x. Okay, here's how my brain is braining it. What's the derivative of cotangent of x? Gotta remember it. The derivative of cotangent of x is negative cosecant squared of x. Great. So the derivative of cotangent of x is negative cosecant squared of x. The derivative of cotangent of some stuff is going to be negative cosecant squared of that stuff. But then I said stuff. And if you say stuff, what do you have to multiply by? The what? The what? You're missing a word. It's an important word. The derivative of the stuff, right? It's always the derivative of the stuff. So we're going to multiply by 4x cubed plus cosine of x, the derivative of the stuff. Cool. Why don't you guys try this next one? I want you to find the derivative of, sure. Let's do cosine of x to the 8th plus x to the 4th plus, sure, secant of x. Yeah, it's a little gross. It's not that gross though. You can do it. Just as a reminder to everyone, at some point, you're all welcome to pick up one of these handouts in front here. It's just a lot of derivative questions with lots of the product chain quotient rule on front, and then lots of answers, not solutions, but answers on the back. If you want solutions, come see me. I'm happy to talk about any of them. I'm gonna talk about implicit. All right, time's a wasting. So I know the derivative cosine of x is negative sine of x. I really want to emphasize how much I really do think about it like this, right? I'm really not thinking about the derivative cosine of gross thing over there. I'm thinking about the derivative cosine of x. I'm like, okay, derivative cosine of x is negative sine of x. I do think it's good to say the x. Like I've over the years, I've really wanted people to be like, don't just say cosine. Say cosine of x. There always has to be something you're taking the cosine of. And the word of actually is important because when I hear the word of, it makes me think I need to use the chain. I got the derivative of cosine of some stuff. I know the derivative of cosine is negative sine. It's broke the rule I said I should break. I know the derivative of cosine of x is negative sine of x. The derivative of cosine of some stuff is negative sine of that stuff times the derivative of all that stuff, which is going to be 8x to the 7th plus 4x cubed plus secant of x times tangent of x. Here's one that I think is kind of weird. Derivative of secant of 2x cubed plus 9. Okay, so most of the time, when you're finding the derivative of a function of some stuff, that stuff only shows up once. secant and cosecant are exceptions to that general idea. The derivative of secant of x is secant of x times tangent of x. The derivative of secant of some stuff is secant of the stuff times tangent of the stuff. What do I have to multiply by? Thank you, which is 6x squared. Notice I didn't put parentheses around 6x squared because it's just one term. I could, though. It would be fine to write parentheses there. But I wouldn't. So when you have secant of some stuff, the derivative is secant of the stuff times tangent of the stuff times 6x squared. Please. I hesitate to even write this, but I'm going to write it anyway. Don't write secant tangent of something. You have it's secant of something times tangent of the same something. Cool. Yeah. Okay, one more, and then we'll talk about some other things. So they can be more complicated. You can use the chain rule many times. Like, for example, the derivative of, cosecant to the 6th power of x to the 4th. Why always 4, James? 4 is like x to the 14th plus sine of, making it really terrible, sine of 3x. Okay. So when I'm looking at this, I'm trying to kind of identify my outermost function. It's not cosecant. The outermost function here is actually being raised to the 6th power. When I have a trig function to a power and I'm taking the derivative of it, I highly recommend rewriting it as the derivative of cosecant of x to the 14th plus sine of 3x, all raised to the 6th power. So then it's a little more obvious that, oh yeah, I've got a bunch of stuff to the 6th power. Okay, let me show you how I do it, and then let me break down the steps. So if I've got something to the 6th, the derivative is going to be 6 times that stuff to the 5th power times the derivative of the inside stuff. Oh boy, it's going to get messy. The derivative of the inside, well, the inside is cosecant of some new stuff. And the derivative of cosecant of x is negative cosecant of x times cotangent of x. So the derivative of cosecant of some new stuff is going to be negative cosecant of the new stuff times cotangent of the new stuff. Did I leave myself enough room? Maybe. X to the 14th plus sine of 3x. Sorry, that's gross. Let me zoom in so you can have a chance of reading what I'm writing. And then cotangent of x to the 14th plus sine of 3x. Okay, but that was the derivative of cosecant of some new stuff, and I got negative cosecant of the new stuff times cotangent of the new stuff, and then I have to multiply by the derivative of that new stuff. The derivative of x to the 14th plus sine of 3x is going to be 14x to the 13th plus the derivative sine of 3x. Oh, that's sine of some stuff. Derivative sine of some stuff is cosine of the stuff. Oh, you can't see it, sorry. Times the derivative of the stuff. Notice that that 3 is only multiplying the cosine of 3x. We could have done this in a lot more steps if we had wanted to. We could have said first it's going to be 6 times cosecant of x to the 14th plus sine of 3x, all raised to the 5th power, times the derivative of cosecant of x to the 14th plus sine of 3x. And then we could have been like, okay, now I'm going to take the derivative of cosecant and get, it's a lot of writing. So this is why I don't usually like doing it this way, because it's a lot more writing, but it's also perfectly fine to do it. I would recommend at first doing it this way, where you're writing out a bunch of steps. Eventually you will get tired of doing that and be like, well, okay, I know how to take the derivative of this thing. I'm not going to write out the thing prime, and then in the next step, I'm just going to do it. But we can do it this way. We did it this way. I'm going to get Okay, so now the derivative of cosecant of some stuff. I know we just did it, but it's going to be negative cosecant of the stuff times cotangent of the stuff times derivative of that stuff. X to the 14 plus sine of 3x. And then finally, you do one more step, which would get you up to this final answer here. 6 times cosecant of x to the 14 plus sine of 3x to the 5th times all that, negative cosecant of x to the 14 plus sine of 3x times cotangent of x to the 14 plus sine of 3x times the derivative of that stuff, which is 14x to the 13 plus sine of 3x. Yeah. Because, so the derivative sine of some stuff is going to be cosine of that stuff multiplied by the derivative of the inside stuff on the derivative 3x. Yeah, sometimes you have like an inner, like secret kind of extra chain rule thing in the middle of your other chain rule stuff. All right, so chain rule problems can get pretty gross. You have to, I would say, take your time, be careful, think about what's on the outside, what's on the inside, and definitely make sure you're leaving the insides as is, and then outside of it, you're multiplying by the derivative. No, I don't want to say that. Okay. Yeah, we should move on to talk about implicit differentiation because you guys have definitely talked about it in class. It's kind of an interesting thing. Implicit differentiation is really just the chain. Chain rule in disguise. Not really even disguised. Sorry. It says implicit differentiation, aka the chain. So here's an example of an implicit differentiation problem. Might try sometime. Sure. Find y prime or dy dx, the derivative of y, for the following equation. Y cubed times x squared plus y to the 4th equal to x cubed plus 9. Okay. I will point out here that we cannot solve for y. You can't just write y equals some function of x. That is usually the case, not always the case when you're dealing with the differentiation. The point here, though, is that y is a function of x, or at least we're pretending like it is. That's actually what we're doing, because it's not always a function of x. So we're pretending like it is. So if you really wanted to, you could rewrite this. And I'm going through this one time, and I'm going to point out that you don't have to do this. I'm going to rewrite this as f of x cubed times x squared plus f of x to the 4th equal to x cubed plus 9. Same deal. Y is a function of x. And now we're going to differentiate both sides. So what's the derivative of some function cubed or some stuff to the 3rd power? 3 times our stuff to the 2nd power, but then I said stuff, so what do I have to multiply by? Which in this case is f prime of x. And then maybe I should have started by saying I need to use the product rule here, because I have f of x cubed times x squared. So I've done the derivative of that part, and then I need to multiply it by x squared. So I'm really thinking of like, this is my g, and this is my h. And here's my g prime. Here's my h. And then I have to go the other way and leave g alone. We've got f of x cubed times the derivative of x squared, which is 2x. Here's my product rule of that first piece. Definitely a product, right? I've got a function times a function. I did the derivative of the first part times the 2nd part, plus the first part times the derivative. All right, plus what's the derivative of something to the 4th power? 4 times my stuff cubed times the derivative of my stuff equal to the derivative of x cubed, which is just 3x squared. And there's no having to multiply by the derivative of x here, or there is, but the derivative of x is just 1, plus the derivative of 9, which is 0. Okay, but no one's actually writing it this way. What people are actually going to write instead, pretty much the same. What they're really going to write is 3y squared times y prime times x squared plus y cubed times 2x plus 4y cubed times y prime equals 3x squared. Because we don't want to write f prime of x to the whatever. Like it's easier to write y prime, or some people like to write dy dx. So that's the idea, is that when we're taking this derivative here, the y is our quote unquote stuff. Y is some function of x. When you take the derivative of y cubed, you get 3y squared times y prime. After you've done this, the rest of this problem is algebra. We have to solve for y prime. So I'm going to identify my terms that have y prime and collect them all on one side. Great, they're already on the left. And then everything else is going to go to the other side. So I'm going to rewrite this as 3y squared times y prime times x squared plus 4y cubed times y prime equal to 3x squared minus, I'm going to rewrite this as 2xy cubed. Then I'm going to factor out a y prime from the terms on the left because every term on the left has y prime. That's why I did that. And y prime times 3, I would write this as x squared y squared because we usually write things in alphabetical order. Plus 4y cubed, still equal to all that. 3x squared minus 2xy cubed. And finally, I would divide both sides by that to get y prime equal to 3x squared minus 2xy cubed divided by 3x squared y squared plus 4y. And that would be our answer. So the idea with implicit differentiation is that we are thinking of y as a function of x. We're not explicitly, that we're implicitly, we're not able to explicitly write y as a function of x. It's implied that y is a function of x, but it is not actually a function of x. So this is kind of the gist. Let's look at, we got time, right? A little bit of time. Let me look at another example because sometimes people are going to, there's so many things to talk about. Yeah. Sure. So give me a few minutes. Here's what I really want to say because I think it's worthwhile. She talked about in class the derivative of e to the x and natural log of x, and maybe gave some justification for them, but there are a couple ways of doing it that don't require. I'm just saying what it is. Well, sorry, yeah. Yeah, sorry, I want to cram in like 10 more things, but we only have like 5 more minutes. So here's what I want to point out. We definitely have the derivative of e to the x is e to the x. And also, so you can kind of get one from the other. What do I mean by this? Well, what if I want to take the derivative of the natural log of x? I could do it like this here. What I could also do is I could say, well, let y equal to the natural log of x. Okay, fine. And then I'm going to rewrite this. E to the y equal to e to the natural log of x. Or e to the y equal to just x. Now we're going to use implicit differentiation on both sides. Or just differentiation, but it's implicit because we don't have y kind of isolated here. So I'm going to ask a question I don't want to ask. What's the derivative of e to the y? Or better question, what's the derivative of e to the stuff? Right, e to the stuff times the derivative of the stuff. Just like the derivative of e to the x is e to the x, the derivative of e to the stuff is e to the stuff times the derivative of the stuff.
For writing and then x, is it same as 1 over x percent
So be careful here. I know what you're trying to say, but I don't want to use the word the same because it's definitely not true. Right? Natural log of x is not the same as 1 over x. What I think you mean is that the derivative of the natural log of x is 1 over x. So when you mean something's the derivative, it's really important to say that word. Just like we definitely don't want to say x cubed equals 3x squared. We know they're not actually the same. I know what we mean is that the derivative of x cubed equals 3x squared, but I really encourage you to use the word because it'll help you remember that's what you mean. So let's see here. I take the derivative on the left-hand side. What's the derivative of x? And now if we solve for y prime, look what happens. Y prime equals 1 over e to the y. But then look here. E to the y is equal to x. So really, we get, as you were saying, y prime is equal to 1 over x. And since y was natural log of x, the derivative of y, or the derivative of the natural log of x, is 1 over x. So it really is true. The derivative of the natural log of x is 1 over x. And then you might ask, well, James, how would you show the derivative of e to the x is e to the x? And be like, well, we don't have time for that. Actually, we do, but it's always yeah. Anyway, so what I want to point out, with like 1 or 2 exceptions, we've really written down almost every derivative formula you are expected to know. So just like before, there is a chain rule version. So there's always a chain rule version of your formula, of your derivative. For example, we just had the derivative of e to the x is e to the x. So what's the derivative of e to the x cubed plus cotangent of x? Well, the derivative of e to the x is e to the x. So the derivative of e to the stuff is e to the stuff times the derivative of that stuff, which is going to be e to the x cubed plus cotangent of x times the derivative of x cubed plus cotangent of x, which is 3x squared minus cosecant squared of x. In a similar way, the derivative of the natural log of x is 1 over x. The derivative of the natural log of some stuff, like x to the 5th plus cosine of x, well, that's going to be, your natural log of x is 1 over x, the natural log of stuff is 1 over the stuff times the derivative of the stuff, which is 5x to the 4th plus negative sine of x. Should try to write just minus sign, but you've already written the plus sign. So right, every derivative we know, x to a power, all the trig functions, e to the x, natural log of x, they all have nice chain rule equivalents. Which is just if you replace the x with some stuff, the same rule applies, but then at the end you always have to multiply by the derivative of the stuff. That's kind of the big picture when it comes to the chain. And then it gets more complicated if your functions are more complicated. But really at a very base level, we can always be like, oh yeah, the outer function is this, takes derivative, leave the inside alone, and then after that, multiply by the derivative. All right, I know it's been a lot today. It'll be a lot on Thursday as well. And then you guys have a midterm next Friday, right? Okay. So yeah, Thursday we'll talk more about implicit. I know we just did that one example. Yeah. All right, take care. Do lots of practice. That's really the only way to get good at it, is to practice these rules a lot. You definitely need to practice them a lot because you're going to use them a lot next quarter too. They're never going away. Derivatives are like going to be with you throughout the rest of your math career. So for as long or as short as that may be, really, I can't stress enough how much you need to practice these rules. Like practice so much. Please, for yourself, do it for you. Okay, that's all. I'll say anything on Thursday. What's up?